L be a real number. Given those parameters, the limit as x approaches a of f of x equals L if, for every epsilon greater than 0, there exists a delta greater than 0, such that for all x, when x minus a absolute value is less than delta, then f of x minus L is less than epsilon. So I've given you a picture of that, and hopefully that is clear now. When we come to this, we're saying when when x is within a of delta, when x is within delta of a, that's what this means, then over here, f of x is within epsilon of L. So we have this dance. We're picking our y's closer and closer to a to establish what we need and are within epsilon of L. All right, let me show you an example, and it won't really hit home until you're able to do your own examples. So I'll do one and see if you can do one. Using the definition of limit, let's find the limit, or prove that the limit as x approaches 5 of 3x plus 2 equals what we think it is. So this is straightforward substitution. When we put 5 into 3x plus 2, we get 17. So now I'm going to use the definition of limit to prove that 17 is indeed the limit. To do that, I have to find a rule, a delta for any epsilon. No matter what epsilon I give you, you have to give me a rule for delta that will get me within epsilon of L. So here's how I'm going to do that. First of all, here's what's going on in our thoughts, which is probably the most important part. So this is sort of my scratch work. And I'm going to work backwards to find that there is such a rule for delta that will get me within epsilon of L. And here's how I do that. I'm going to start on this side. So putting it in, here's what I have to prove. Let me give myself a little bit of, according to this definition, this line, I'm going to restate this line in terms of this example. So when the absolute value of x minus, what's our a in this problem? We're approaching a, so it's right here, 5. So whatever we're approaching will show up there. When that is less than delta, see how I grabbed that? I think it's still visible. Then the function f of x, which we know, this is our f of x, 3x plus 2 minus L, which is, this is our L, we decided, is 17, must be less than epsilon. Alright. That's what I have to work with. In this specific example, taking the last line of our definition and putting in the values from our problem, we have this. So, how can I find a delta that will always guarantee to be within epsilon of this limit 17? What I'm going to do is work backwards. So I'm going to start with this, and I'm going to indicate that the absolute value of 3x plus 2 is minus 17 is less than epsilon, and I'm going to work backwards to find out what delta must be. Alright, so let's simplify within the absolute value sign. What is 3x plus 2 minus 17? It's 3x minus 15. And that is absolute value. Let's remove the absolute value symbol, and we can do that with a compound statement like this. That tells us that epsilon, negative epsilon, is less than, no absolute value sign, 3x minus 15, which is less than positive epsilon. That's how you take a statement in absolute value, which you learned in Algebra 2, to how to remove it and have an algebraic statement without absolute values. So it's going to involve that negative epsilon and a positive epsilon. Right now, in my thoughts, I want this to appear inside of this some way. So let's let's factor out a 3 from the middle. See how I'm aiming for an x minus 5 in my backwards thinking. So now divide everything by 3. I get negative epsilon over 3 is less than x minus 5, which is less than epsilon over 3. And in inequality, when I divide everything, every section has to be divided by 3. Alright, so observe what I can rearrange that and put absolute value back in. So this is the same way as saying is absolute value of x minus 5 is less than epsilon over 3. So look at the match. I was aiming for a match. So this tells me that I can take delta and call it epsilon over 3. So whatever epsilon you give me, that's how close I want the limit to be, even if it's very small. All I have to do is take that epsilon that you demanded of me and divide it by 3. And it will always get me within epsilon of that limit. So we have proven then that it is the limit. L, or 17, is the limit. So this was our scratch work. So let's do the proof. Forward march. So this will be over here. There's a little space left. Alright, so here's the actual proof. We're going to start from this side, because that's how the statement runs, and we're going to say when for some epsilon greater than 0, let that be given, and we are going to choose delta to be epsilon over 3. When we have this relationship between delta and epsilon, we are on a good path. So we start again on this side, and if it leads to that side, then we know we have found the limit successfully. So I'm going to start with the absolute value of x minus 5 is less than delta. And I'm going to use this substitution. Instead of delta, I'm going to use epsilon over 3. And I'm going to remove the absolute value sign. Remember, that creates a negative absolute value over a negative epsilon over 3 is less than x minus 5, which is less than positive epsilon over 3. And now I'm trying to get this to look like this. So I'm working in the forward direction, excuse me. So we have, we're up to here. So I'm going to multiply everything. And so we're here and we're trying to get to here. I notice a 3 in here. So I'm going to multiply everything by 3. Somewhat backwards to what we just did on the other part in our scratch work. And